Everybody, thank you for joining today's Kubernetes Clinic. Today's title is Building Stability, a live demo of pitfalls when resource requests and limits are not set. Today's featured speaker is Andy Suderman. He's the Director of R&D and Technology at Fairwinds. As a reminder, today's session is in listen-only mode. If you do have a question, please submit it through the Q&A tab in the lower right-hand of your corner. Andy, over to you.
Thanks, Dave. As the title implies, today I'm going to talk a lot about resource requests and limits. It's a topic that's sort of near and dear to my heart because I feel like it's kind of the base for stability in a Kubernetes cluster. It's something that is easy to get wrong, easy to forget, and can have very interesting and far-reaching effects. So the goal of the session today is I want to show what happens when you don't set your resource requests and limits correctly. So I feel like we spent a lot of time talking about, saying do set them. And, we may know one or two things that happen when we don't set them, but we don't necessarily always fully explain why this is important and what effects it can have on the cluster. So I'm going to do a series of demonstrations where I'm going to tweak some settings in my cluster, see if I can break some things and kind of show what happens when we do stuff wrong and what happens when we do stuff horribly wrong. And as Dave said, please feel free to throw questions in the Q&A. I'll keep an eye on it. I think he's going to help me keep an eye on it as well. Happy to mix in plenty of answers to those questions while I'm doing these demos. So let's get the screen share going here. And there we go. All right. Hopefully everybody can see that. And so everything I'm going to do today is contained in this GitHub repo. It's in the Fairwinds Ops organization in GitHub. It's called Resources Demo. So github.com/fairwindsops/resources demo. Dave, actually, if you have a chance, if you could throw that in the chat for folks, that would be super helpful. So first, let's talk about the setup. What do we have here? So what we have is a GKE cluster. It's on 1.21.6. We are running N2 standard nodes, N2 standard 2 nodes. So we have 2 CPUs and 8 gigs of memory per node. We have node autoscaling enabled with just 1 to 2 nodes per zone and 3 zones. So that means we can have up to 6 nodes at any given time, and autoscaling is enabled. In this cluster, I have installed an application. So we have a demo application. There is a link to the source code for this, and then the YAML to deploy it is in the repository that I just talked about. In that repository, there's some links at the bottom. That includes the link to this app that I'm using, and then some of the other tools I'm going to use today as well. So we have this app. It's a multi-tiered web app. So we have this front end. We can vote for where we want to go to lunch. There's a database. There's a Redis cache, and then there's a backend that this talks to as well. So there's a few components to this application. I'm just exposed it via a load balancer. So nothing fancy going on here, just a pure load balancer. And yeah, that's the setup. So the first thing that we're going to do is show what happens when we don't set requests and limits at all. So I have my app running. If we look at my app, and I'm going to focus on the app server, which is the back end of this app today. And if we take a look at this in the resources block of this spec, we see that we have set requests and limits. So we're requesting 200 millicores, and we've set a limit of 200 millicores, and we're requesting 100 megabytes of memory, and we have a limit of 100 megabytes. So what I'm going to do is, let's say the scenario is I'm running this app, I'm responsible for it. Someone else is also deploying into this cluster, because that's pretty common, and multiple teams deploying into our clusters. And someone else comes along and installs another application in the cluster that doesn't have any request or limits set. So it's just going to go hog wild and try to eat all the resources in the cluster. So in demo1.course.yaml, we'll see this is a Reckoner course YAML. It's an open source tool we have that just wraps Helm. We're going to install a couple of Helm charts, and I'm going to install a CPU stress and a memory stress. This is a container that just comes up and eats memory or eats CPU, uses the Linux stress command to do that. And we're going to run 8 replicas of those. And I'm going to fire that off in its own namespace real quick. So I'm going to plot course.yaml, which is equivalent to, find the name. There we go. This is equivalent to a Helm install of those 2 charts. So we're going to start installing those. And at the bottom here, I have a nifty tool running. It's called K9s or K9s, I'm guessing is the appropriate way to pronounce that. And we see here the 2 app server containers running. We see our DB container, we see our UI container, and we see our Redis server. And so that's the Yelp namespace. The nice thing about this view is that we can see the percentage of the memory request, memory limit, and CPU request and limit that we're consuming at any given time. So right now there's no load on this app. It's just sitting there statically. The only load I've generated on it is probably going and clicking these buttons like I did earlier. So the last component we have is a tool that we're going to use to sort of benchmark and test. And so I'm going to use a tool called K6 made by a company called Load Impact. And we have this load script. It's, I'll just cat it out real quick. It's in the repo. It's JavaScript. What this does is it goes in, it loads the main page, and then it clicks on each one of those buttons once. And that would be called an iteration of this test. And so I'm going to K6 run load.js. That is configured to automatically do 10 of those iterations and amongst 10 virtual users, as they call them, which means I'm going to run all 10 of those tests in parallel. And we see here we have an iteration duration of 5 seconds or 5.9 seconds. And we have our HTTP request duration at an average of 140 milliseconds. So I know, because it's my app, that's kind of the baseline, pretty close to the baseline for how this app should perform with no load and nothing going on in the cluster. We may notice that K9s has just started getting upset. It says something about a critical CPU level. So let's go take a look at what's going on with the namespace where I just installed these stress containers. So we're going to get pods. So let's use K9s to do this. Go to namespace. We're going to go to the stress namespace, and whoa, as expected, as I expected, we have a lot going on here. We have a lot of evicted pods. We have, because of that, we have a lot of pods pending and coming up. And so let's just describe one of these and see what's going on with it. Let's look at the events here. This was evicted because the node had conditioned memory pressure. So what's happening is that this app that's allowed to consume all of the memory and CPU of all these nodes has just taken all the resources of the node. But the cool thing going on here is my app's still working. So we've just effectively, consumed all the resources in the node. If we go look at nodes in the cluster, we'll see that we're using all the CPU and a good portion of the memory on a lot of these nodes. But my iteration duration is still at 5 seconds and my request duration is still under 100 milliseconds. That's because I have specified my memory requests and limits on the app that is critical. And I've done them in such a way as to be to provide what's called a guaranteed quality of service class. So when we set our requests and our limits to the same numbers, we get a guaranteed quality of service, which means the Kubernetes, the scheduler, and well, not just the scheduler, but the that C group is going to be given higher priority than another one, which is why we see all of these pods getting evicted in the stress namespace, because these don't have memory requests and limits. So if you want something to keep running, even when you have noisy neighbors in your cluster, you have things trying to break your cluster, like I'm doing in this scenario, you can still keep your critical apps running and functioning. If we go back over here, we can reload this app. We can load the number of total votes that have come through. We can click on things. It's still working just fine, even though this cluster might be in what is considered a not great state. All right. Another thing to note here, if I don't have resource requests and limits set like on this stress app, if there's some sort of horizontal pod autoscaler on my app, it's not really going to function because that's going to generally be some sort of percentage of my request. And so that's not going to function as well. All right, so that does it for the first demo, I think. I don't see any questions. Again, feel free to ask any questions you might have. I'm happy to answer them. So I'm going to delete that stress namespace, which will get rid of that Helm chart that I installed. Another thing to note, we did manage to scale up our cluster. GKE autoscaling is a little bit more intelligent. It saw the node pressure for CPU and memory and scaled up. If we were using something like the cluster autoscaler, it's based on whether there are pods pending or not. And depending on the life cycle of these evicted pods and how quickly they were coming up and going down, we may not have ever actually triggered a scale up in this event either. So yet another reason why it's super important to set at the bare minimum a CPU and memory request so that we can get scheduling figured out. We can figure out where to put these nodes. It can trigger scaling if need be. We can horizontally auto scale and things like that. All right, I'm going to give it just a moment for this cluster to stabilize. Wait for the node CPU usage to go down. Looks like we're already getting there. I'm going to run my load test again. We're going to just check this baseline, make sure we're still down at about 5 seconds per iteration and under 100 milliseconds for our request duration. It looks like we're well under that, so that's good. That's good. All right. So that's the first scenario. That's kind of worst case. You don't set resource requests and limits. Things get evicted. They get killed. You blow up your nodes, all that sort of stuff. That's the first demo. Now we're going to move on to the second one. This one's a little bit more interesting and a little bit more complex, a little bit harder to necessarily fully grok. But this is when you set your CPU limits too low. And so what happens when you set your CPU limits too low is we start to see CPU throttling. The Linux kernel is going to limit the amount of CPU cycles or CPU time that your process can use. And this can have a lot of really difficult to anticipate effects in your cluster. So the first thing I'm going to do is I'm going to go back to my app. So let's go back to the Yelp namespace. And we're going to look at deployments in this namespace. And so we have our app server here. And I'm going to edit this directly in the cluster. And we're going to find the resources block here. And I'm going to turn, so maybe I just deployed this app. Maybe I don't know how much CPU it needs. I'm just going to put it down at 10 millicores. We're going to turn it all the way down. We're going to see what happens. All right, we see we have a container being created with this new setting. We're going to check the logs on that. Container's still waiting to start. Give this just another few moments. Taking its time. All right. We've pulled the image, so that's done. It seems to be running, but it has not gone into a ready state yet. So its readiness probes aren't passing, but it is at least attempting to run. All right, let's check the logs again. Looks like we don't have any. Let's describe this real quick and we'll go down to the events. And oh, there we see a problem. We have liveness and readiness probes failing all over the place. So that's happened 5 or 6 times. If we wait just a little bit longer, this pod is going to get restarted because it will have failed its liveness probe too many times. And still we have no logs. So this container is running, but it doesn't seem to be doing anything. And this is because it's being CPU throttled. It literally can't even begin to start up because it can't get enough CPU time to do what it needs to do. So what's going to happen is this will never go into a ready state. It'll get killed, and then it'll just sit here, and this rollout will never succeed because the pod can't even start. So if you see a situation where your liveness probes or your readiness probes are intermittently failing or unexpectedly failing, there's no log information about why. A lot of times this can be due to CPU throttling. Obviously, this is an extreme example where I've throttled way down to 10 millicores and the pod can't even start, but I have also seen this happen at higher levels and happen intermittently as well. So we see now we have one restart. We're attempting to use 110% of our CPU requested limit right now, and it's just not starting. So we're going to go back to our deployment, and we realize that maybe 10 millicores was a little too aggressive. So let's bump that up to 40. Let's quadruple the amount of CPU we give this thing. And let's take a look and wait and see what happens with this newest container. All right. The old one's going away now. That's fine. That was our failed attempt at 10 millicores. We are still container creating here. Oh, we've gone to a running state. We still don't have any logs. Let's describe that. And let's see, we have one liveness probe failure. Just one failure is not necessarily a problem. We are actually seeing logs now. So Sinatra has started, and it looks like now I know the probe for this is on the API get stats endpoint. So we are actually serving requests. So that's gone into a ready state, and now we're going to finish our rollout. So the next one's going to come up. We've started terminating old ones. So we've at least gotten to a point where our application can start. But now let's take a look. Well, let's wait for this to finish rolling out. But what we're going to do is we're going to take a look and see how our app is performing. We know from this example and what I did in the last test, we have a baseline performance for when the CPU requests limits are much different. So let's go ahead, and now that we have 2 of these new pods in the running state, I'm going to run my load test again, and we're going to see how we're doing against our predetermined metrics, our performance criteria here. And we're already up to 10 seconds. So I know this is going slower than it should. The previously finished much quicker. So we've effectively doubled or higher our iteration duration, and our request duration's up to 558 milliseconds. So we have taken a serious performance hit here, by throttling down our CPU. So if you set those limits too low, then you're going to see throttling, and that can negatively impact your application's performance. In this case, significantly negatively impacted it. All right. So let's go back. We know that 40 is too low. Let's see if we can get the performance a little bit better. Let's go back up to 100. Let's go up to 100. Let's see how we do with that. All right. Wait for that rollout to finish again. Got a new container coming up. Our old one is terminating. Got another one. And go ahead and run our test here in just a moment. There we are. Got 2 of the new ones are ready. We'll run our test again. See if we've improved our performance. All right. Our request duration is down to 179. So we've gotten much better on that. And our iteration duration is still down to 6 seconds. But we still haven't hit that sub 100 millisecond level that we're looking for. So let's run this for a little bit longer and keep some load going on it and see how much CPU we're actually using while we're doing this, because I am curious to see if we are using all of our CPU limit or not. Because CPU throttling, because of how the calculation is done, can happen at different percentages of the CPU limit. And I don't claim to fully understand the mechanisms and the calculations that go into it. There's some really good videos online about how this works. But understanding that just because you're not using all of your CPU limit doesn't mean you're not being throttled. And so there are ways to monitor throttling in your monitoring solution of choice. Whether it be Prometheus or Datadog, there are metrics for CPU throttling and then percentage CPU throttling. And so something to keep an eye on, something to look at if you're seeing negative performance implications from this. Now, I'm not saying you should just go up your CPU limit because you're seeing CPU throttling, but you should be monitoring your application's performance metrics, right? In this case, I'm looking at HTTP request duration, trying to get that down below 100 milliseconds. When that is suboptimal for me, then CPU throttling is one of the things that can cause that suboptimal performance and maybe something that I should look at. So here I'm at 70 or 80% of my limit on CPU, but not 100%. And we're still seeing some CPU throttling and negative performance because of that. So what I'm going to do is, actually, I'm just going to put this back to the way it was when we started. And then we're going to run our load test again and just make sure we're back to that sub 100 milliseconds. All right. Yep, now we're down to 83 milliseconds and 5-second iteration duration. So that's looking really good. All right. Still don't have any questions. Reminder, please feel free to ask all the questions that you might have. I'm happy to answer them. I think now's probably a good time to do our polling question. Dave, did you want to do that? Great. So we have a polling question up. Thank you. Let's see. All right. So the question is, what is your greatest opportunity to improve your Kubernetes environment? First, getting help with the basics, or general best practices assessment, or improving the security posture of your clusters, or saving money, or improving the reliability of apps running in Kubernetes. All great things to be worried about. Which one is your greatest opportunity to improve?
We'll leave it open for another 10 to 15 seconds. Andy, I was going to ask you at the beginning, you mentioned me putting a link in the chat. I just wasn't sure which one it was. I can do that for you now.
Great. Actually, I can do that. There we go. Thank you for reminding me. I meant to put that in there. That's the link to the GitHub repo. I'm running on a branch today. I'll probably merge that after this demo, but that link will take you directly to the branch that I'm using for today's, which also has the polling question in it if you are curious.
All right, just about to close the poll. It looks like we get 50% are looking to improve the reliability of apps running in Kubernetes, about 30% improving the security posture of their clusters, and about 20% getting help with the basics.
Great, great. Well, getting help with the basics and improving your reliability are two things we'll definitely cover today. Security is obviously something else we cover frequently in other webinars, so we won't cover it today, but important thing to talk about. All right, let's move on to the next demo. This one's a lot simpler and easier to understand and a little bit more obvious when it happens. So this one should go fairly quick. What happens when we set our memory limits too low? I think, most people are probably familiar with this one. If you have not seen the phrase OOMKill at any point, I would be surprised. It's a very common thing to see in Kubernetes. So I'm going to turn my memory limit way down, all the way down to 10 megabytes on these pods, and we're going to watch them try to start up. And the nice thing about OOMKill, unlike CPU throttling, is that it is shown in the API. So if you're watching, you may see on my screen here, the status of this pod has just gone to OOMKilled because it has attempted to exceed its memory limit and it has been killed. And so if we describe this pod and we look at the last state, we can see that the reason is OOMKilled. And then the other important thing to note is that the exit code is 137, because there are other mechanisms by which a pod can be OOMKilled or the process can be OOMKilled underneath the Docker container. And so sometimes you'll see an exit code 137 without an OOMKilled reason, which is an interesting thing to see, but always know that that exit code 137 pretty much always means OOMKilled. We ran out of memory, we exceeded our limit, our pod was killed. Very easy to observe, very easy to understand. So that one, I'm not going to spend a ton of time on because I think we're all relatively familiar with that one. All right. So we'll let this stabilize again. For the next demo, I'm going to make some tweaks to our application. And so for this next one, I'm going to introduce horizontal pod autoscaling. So if we look in the app namespace, there's a horizontal pod autoscaler for the app server. Right now, it's just pinned at a min of 2 and a max of 2. I'm going to bump that up to 200 so we can scale up to 200 pods. And then the other thing I'm going to do is I'm going to edit the deployment app server. I'm going to edit the resource requests and limits again. So what we're going to do in this case, and this is probably one of the more common mistakes that I see across a lot of clusters, is what happens when you set your resource requests and limits really far apart. So what I'm going to do is I'm going to set the CPU request to that 10M. That 10 millicores. We know for a fact that this app needs more than 10 millicores. We showed that 2 demos ago when we saw that it couldn't even start up with a limit of 10 millicores. So we know that it needs more than that. Actually, if we look at it running in steady state right now, and we generate a little bit of load against it, let's let that run for a minute here. We'll see that the CPU usage goes above 10 millicores. So I'm going to set the request to 10, and I'm going to set the limit to 500 millicores. So it's allowed to consume up to half of a CPU. I'm going to do a similar thing with memory. I'm going to set the request down to 10 megabytes, and I'm going to set the limit up to 200. So this is requesting 10 megabytes. We know that it runs at about 30, just looking at it in steady state here. So we know it needs more than that. All right, so those are the primary changes I'm going to make to the application. And I'm going to apply that to the cluster. And we're going to take a look at what effect setting these requests and limits so far apart has on our cluster. All right. And then I'm going to just keep run and load at this while we're doing this. I'm going to up the number of concurrent users to 20 just to kind of make this a little bit more exciting, make things happen a little bit faster. We can see if we go back and look at our app, this number probably jumps quite a bit. You know, we added about 3,000 votes here. So this thing's seen quite a lot of traffic during this. All right, we see our HPA is still in an unknown status. We're still waiting for metrics to come in on these new pods that we just spun up. But and this was the number we were looking for. We're using about 83 millicores of CPU at load. So we know that this probably under load, these things can consume 100, 200 millicores. I think we went up to 300 for the defaults. And so that 10 millicore requests is just a little bit ridiculous for sure. So let's watch our HPAs here. And just waiting still. There we go. All right. So the first very obvious thing that we're going to notice is our HPAs, our horizontal pod autoscalers, are going to go a little bit wild. So we see that our target of 50% CPU utilization, we're at a cumulative total of 1,750% of that. And so we're very aggressively going to see scaling here. You can see in the bottom view here, we've just jumped up to 16 pods in the app server deployment. And that's just going to keep going up until we've stabilized closer to that 50%. So it's important to note that your horizontal pod autoscaler target, if you're scaling on CPU, is related to your CPU request, not your CPU limit. And so if we set that limit, that request way too low, we're going to scale far too aggressively with our horizontal pod autoscalers, and we really don't need to. If we look at the CPU utilization of these pods here, there's only one that's over, any amount of CPU usage. But because we set our request too low, we're scaling way too much. So this can lead to excess cost, too big of clusters, all sorts of things. So that's the first very obvious issue we have when applying a setting like this. The second one, the next one that we can see is our overall node allocation. So one tool that I like to use here to demonstrate this is called Cube Capacity. It was written by an old coworker of mine, Rob Scott. And what it shows you is the cumulative CPU requests and limits and memory requests and limits for your nodes. So we can see we have 5 nodes in the cluster currently, and our CPU requests are at an average of about 40% of our node, whereas our CPU limits are up to 500, 400, 300% of a node, which means that we have a potential to try to consume 300% of a node. Well, obviously you can't consume 300% of a single node. And so we'll start to see pressure from CPU on these nodes, and we'll start to see more throttling because as overall utilization goes up, throttling also goes up. And we'll start to see degraded performance. If we go down and well, we can actually just pass the -u flag, the dash usage flag to cube capacity, and we'll see what we're currently utilizing. We're not overutilizing any nodes yet, but because these limits are so high, we definitely have the potential to do so. And we could probably force our hand by upping the amount of traffic we throw at this thing. And let's go look at nodes here. And take a look. We can watch our CPU usage here. Ideally, as part of this demo, we'll start to see these nodes get completely utilized. This is also a big problem with memory, and it's really more of a problem with memory than it is with CPU. If we start to try to utilize 150%, 200% of a node's memory, we're going to start to see a lot of things that are lower priority get evicted in the cluster because we start to get memory pressure on the nodes. So we really want to look at our overall allocation across our cluster and keep an eye on these numbers. If we're starting to see numbers of 400, 500, 600%, this is likely going to lead to a problem down the road for us, especially if we do it across a large number of apps. I personally prefer for any critical workloads to use the guaranteed QoS class that we talked about earlier, where we set them both the requests and the limits the same. It gives it the highest priority and it makes sure that things are working. But I do understand that there are situations in which you might want a workload to be burstable, and that's totally fine. to define that term. Burstable QoS classes when we set the resource requests and limits differently. We set the limits higher. You can't set them lower. It's impossible. And so your app is allowed to burst up into that higher amount of resource utilization. But in general, I would say, I think in the last time I gave this demo, someone asked if we should like what percentage we should aim for, what kind of standard we should go for if we're using the burstable QoS class, and it's going to be different for every workload and every situation and every cluster. But I would say, 10 to 20% is probably a decent cap on how far you want to set those apart. And so I think defining that for yourself in your application across your clusters, across your organization, saying we don't want to be able to burst more than 20% will help a lot with the reliability and stability of your clusters. And then the other thing that gets impacted when we start to run really low requests and high limits is scheduling. So when the scheduler chooses what node to put a pod on, it will do this based on the request, not the limit. And so we can see situations where, maybe there are 10 millicores available on a node, but only 10 millicores. I schedule this pod there. Well, now it's suddenly in a situation where there's not enough CPU to go around. And so our scheduling algorithms get a little bit unhappy or confused by this. And so it's much better to keep those requests and limits closer together so that we actually have reasonable scheduling across them. So that's my last demo. We talked about, again, just to recap, what happens when you don't set your resource requests and limits. So we allowed a pod to consume all of the CPU and memory, and it was evicted because there was no CPU and memory pressure, but it did not impact our application, which was using a guaranteed QoS class. Second, we set our CPU limits way too low and started to look at what it means to experience CPU throttling, seeing our probes fail and seeing degraded performance in our applications. We talked about out of memory kills and what happens when you don't set memory high enough, when you set your memory limits too low. And then the last thing I talked about was setting your requests and limits way too far apart and upsetting the scheduling and horizontal scaling algorithms, as well as introducing the potential for nodes to become overwhelmed in resource utilization. So I hope you all learned something interesting today. As just a quick demonstration, our FAS platform, which integrates some of our open source as well, can demonstrate and detect a lot of these things for you. So we have what is called the workloads report in Fairwinds Insights, and it will show you your applications and take a look at the requests and limits over time. I don't have enough data in here to show this at the moment, but it'll make recommendations on how to set those resource requests and limits. And then you will also be able to see action items that show you both security and reliability and efficiency concerns in your cluster. And you'll get a series of action items that allow you to address those issues. You can filter down to the resource metrics report and see that our memory limits are too high. Excuse me. And we may want to adjust those down based on historical usage from Prometheus. Looks like we have a question in the chat. I can answer that. Have you heard of new capabilities in the marketplace where resource management is turned over to a learning AI module that would learn what the optimal settings would be and then to apply them to apps? That's a great question. And yes, there are some things out in the market that will allow you to run tests. There is one particular application that I have used. It's by a company formerly called Carbon Relay. I believe they're Stormforger now. Forgive me if I got the exact wrong company name there, but essentially what it does is it allows you to specify a setting that you want to change. So say I want to change my resource requests and limits, and then you want to set, because it's a machine learning algorithm, you need some sort of thing that it's trying to optimize for. So you try to optimize for, highest latency and lowest price, and it will run a series of tests and tell you and show you the curves of, here's where your lowest cost is, here's where your best performance is. Now you can choose where the intersection, you can choose to run at the intersection point of those and try to optimize for both. So there are some capabilities out there. I think they're super cool. The biggest struggle with using those types of tools is being able to generate realistic load against your test environment. If you're running these in your test environment, or being willing to run them in your production environment to do these tests. And then also setting them up can be complex, because we need to understand, what are the metrics that we're looking at? Are we actually measuring latency of our app over time? And can we use that to maximize, to optimize our performance? So I do think we'll see more tools like that in the future, but they are tricky and difficult to get working for sure. So, all right. I don't see any other questions. Now's the time to put in your last minute questions if you have any. All right. Well, Dave, do we have anything to wrap up here, or are we all set?
I think we should be all set, Andy.
All right, everybody, thanks for coming to listen today. I hope you enjoyed this. Remember, the code is available in that repository, and the recording of this, I believe, will be available afterwards as well if you're interested in watching it again. And I hope you all have a great rest of your week. Thank you.
Thank you.